Good morning and welcome to day 2 of Chemspec Digital. My name is Christiana, I'm the event manager, and I have the pleasure to introduce our first session in the RSC Symposium this morning. And before I do, I would like to point out that this session is being recorded for it to be available on demand later on the platform. And we do also invite attendees to write their questions into the chat box available on their screen, and we will read them out at the end. But without further ado, I will hand over to Christian Hornung of CSIRO Australia, who will be presenting a 3D printed catalytic static mixers, a new continuous flow solution for hydrogenations.
Thank you very much, Christiane. And thank you for everybody dialing in this morning. It's a pleasure for me to present our work at the Chemspec Digital this year. This is a presentation effectively of the technology that CSIRO has developed over the past few years and is now in the process of commercializing with our partners here in Australia and overseas. And what I'm mainly will be focusing on as part of this talk today is the application of CSMs or catalytic static mixers for hydrogenations in the chemical manufacturing industry. Here we go. So the catalysis and heterogeneous catalysis obviously has many different forms and how it's practiced in industry. Large scale, quite often these solutions include a type of a bed, a fixed bed type reactor, or it can be expanded or even recirculating beds using a form of a structured or particulate form catalyst. And depending on what system is used, quite often what these large scale operations and apparatus suffer from are certain complexities around the fluid mechanics, the mixing inside these larger columns. It can be difficult to thermally manage these catalyst beds. There is the danger of having or producing hotspots in certain areas, depending on the chemistry. Quite often, there is issues associated with high pressure drops that are built in these fixed bed type systems. And that has a whole range of flow-on effects that then are difficult to manage these systems, and also more complex other complexities that come in translating solutions from lab scale to pilot scale and then to final production scale, where quite often at several iterations at these steps, there has to be re-engineering of the system. So what we will try to do is trying to not reinvent catalysis, but trying to see if we have engineering methods and process methods that can make these quite complex heterogeneous catalysis operations more controlled, and therefore much easier to handle, and offer a range of benefits to the chemical manufacturer that is operating these systems. And what we wanted to do is combine a few emerging technologies to see if we can do this better, if we can do the engineering and the process itself better for these catalytic applications. In our case, we combine mainly two steps to make a more structured approach to the catalyst, and that is additive manufacturing. In our case, mainly 3D metal printing, direct metal printing. So we're using either laser printing or electron beam melting. And that is uncoupled with a second step, making these structured catalyst devices, which is a coating step. So on top of a scaffold that would be printed out of a relatively inert material, such as stainless steel, shaped to the geometry to fit inside a chemical apparatus, we would then coat a catalytic active layer with a range of different deposition methods. And then these catalytic inserts, or as we term them, catalytic static mixers, or CSMs, would then be inserted in a chemical apparatus, be it a tubular reactor or something similar, to perform the chemical reaction. A few words on the catalyst deposition methods that we've used. We try to see that from a platform type approach. So not one catalyst and one deposition method can be used here, but a multitude of them. And depending on what types of catalysts we're using, they speak better to one or the other of the deposition methods. The three main methods we've been using so far are on this slide. So for the metal on metal type catalyst systems, so palladium zero coat or platinum or nickel coat, we use electroplating and metal cold spraying. They give very high performance and as well as very good adhesion of the catalyst layer to the stainless steel substrate. And then for more classical catalyst systems such as metal oxides, for instance, so aluminas, ceria, titanium silicates, titania, and many others, including carbon type support systems, again linked with a noble metal such as palladium, platinum, or any others. For these systems, we usually use a wash coating technique that then gives a very well-defined and porous catalyst layer on top of the stainless steel mixer. These two images show some of those catalyst layers. The top is a palladium coat, palladium zero coat on that was done by electroplating. And the bottom is a cross-sectional cut through a porous nickel coat that we deposited using cold spraying onto the 3D printed static mixer. In this case, that was a titanium alloy static mixer. And you can see the porosity inside that nickel compared to the underlying scaffold. Now, how are these systems used in operation? What we use quite often is tubular type reactors, and the main application we've been using, or the main set of reactions that we looked into, are hydrogenations. As hydrogenations are used throughout various different sectors in the chemical manufacturing industry, from making pharmaceuticals, fine chemicals, all the way up to bulk chemicals. So in a very simplistic form, what's shown here is a simple process flow diagram, a simplified process flow diagram, how we run these type of reactions. You'd feed hydrogen gas, in our case, directly from cylinder, into the reactor together with the substrate or the feed that's usually delivered by a pump. So that would be a liquid feed line. Inside the reactor, you will have several reaction chambers or tubes that would be filled with the CSMs. And at the outlet, you would then collect your product. What you see here on this slide is a range of different catalyst coatings that we put onto these cylindrical CSMs. They obviously also can vary in different forms and shapes and particular sizes. So the image here shows two of the standard small scale type CSMs that we're currently working on. The one that's covered in a gold coat here is a 6mm diameter cylindrical CSM, 150mm long, and the slightly larger one is 10mm in diameter. And then you can also use a range of different reactor geometries to operate them. So those are just a few snapshots of the lab systems we operate at our site here at CSRO. Electrically heated, you can use oil heated systems, or in some cases we even used an air heated system for performing these reactions. All of the ones that I show you here are cylindrical geometries. We have printed and made designs also for non-cylindrical geometries, working together with equipment manufacturers that have already a reactor solution in the market. In this case, what we've done is designed a geometry to fit into the air-filled Milprova system, which is a rectangular duct rather than a cylindrical duct. So there we had to change the design slightly to work with a very high aspect ratio, and came up with this corrugated type design that has still a lot of anchor points to coat a catalyst on it. And what you see here in the image is a palladium and aluminum catalyst coated on these flat CSMs. And a last system I wanted to show is the CreaFlow system, which we also have a reactor unit in our labs. And again, this is a flat geometry. The difference to the image before is that in this case, we also have an optical axis. So there's a large window on top of this flow channel, which we use to not only look at our reaction, but also interrogate it this way, but also bring light into the system. So there's a bank of UV lamps that you see here in this particular rig that would shine directly onto the CSM and the catalyst we coat onto those CSMs. And that again is a slightly different geometry there. We've opted for a sand dune type approach that was printed on these CSM strips effectively. And then we coat them with a range of different photocatalysts, such as titania and titania type systems for performing a photo or photothermal process. Now onto some chemistry. This slide is basically just a very brief overview of some of the systems you can look into and that we have evaluated the technology for over the past years. So we've used a range of different substrates that are representative of what industry is currently doing in the realm of hydrogenations. We tested the CSMs for hydrogenations of alkenes, alkynes, various carbonyl groups, aldehydes, ketones, for the reduction of various nitrogen-containing compounds. So those are imines, nitriles, nitro groups, diazo groups. And most recently, we've also been starting to work on some dehalogenations, like as dechlorinations and many others. Now, one of those examples that we've published over the past years is for the applications of making APIs or API intermediates. In this case, this is a study we had done in our lab several years back to reduce these intermediates. In this case, it's a nitro group containing a precursor for the active pharmaceutical ingredient linezolid. And what we've done here is reduce that nitro group down to the corresponding amine using one of our electroplated palladium CSMs. The conditions that we've used here are 120 degrees, 24 bars of hydrogen. And effectively, in this case, that pretty much resulted in full conversion of this nitro group, reducing it to the corresponding amine. You can also see the images here of the highly colored nitro compound that we pumped into our reactor. And then on the other side is basically an image of what came out of the reactor without any further workup. And I should stress that in this case, there was really no workup done. We basically collected the product without any side products and also without any contamination of the palladium catalyst. In this case, it was less than ppb of palladium that we found in our product stream. I'd also like to point to work that was done with some of our partners, especially the group here at Uni Graz from Professor Oliver Kappe, who have been using the CSM technology for a lot of their work most recently. One of the first studies they've done is, again, a similar nitro reduction for another pharmaceutical ingredient, tizanidine. They've used hydrogen in their case not from the cylinder, as we've been using just hydrogen gas. In their case, they had hydrogen on demand system. And rather than using the cylindrical CSMs, they've used the air-filled Miprova system. So they used one of the flat type CSMs coated with a palladium and alumina catalyst. But effectively, a lot of that approach is very similar to what we've conducted in the CSRO labs, and resulted also in very good conversions and high yields. Just to talk a little bit more about the catalyst leaching, I wanted to show this slide very briefly, and that gives an overview over the leaching profiles. As I already said, there's very little leaching that we see, but this paints a bit more of a picture of what kind of contamination or low levels of contamination we actually find in our product streams. So we've done testing. This is usually done by ICP OES or ICP-MS of metal contaminants in the product. And we've done that for all of our catalysts here. We've got a palladium, nickel, platinum, gold, and a rhodium CSM. And what we find in terms of the active catalyst that's coated on top of the mixer scaffold is single digit or double digit ppb contamination, which is very, very little of our catalysts. What you find a lot more is some other metal contaminants, such as nickel, manganese, molybdenum, and also especially iron. And those are all metal contaminations that actually don't come from the catalyst layer. They come from the stainless steel apparatus that we're using. So the flow channel, the tubing is made out of stainless steel, and all the apparatus around it usually as well. And that's where they come from. But it's still in very, very low levels. Those are ppb levels. As comparison, recommendation for pharmaceuticals, for instance, for palladium is 10 ppm, and for nickel is 20 ppm, which we're way below. This is another example of a class of reactions that we've performed using our hydrogenation reactors, where we do a reductive amination. So in this case, you've got two starting materials, or two molecules that you first want to couple and condense into an intermediate imine. And then that imine is then reduced down to the corresponding amine. And that approach obviously gives you the access to much more complex amine type molecules. And we did again a study using our palladium type CSMs for this work, and reacted a range of different substrates. So used different aldehydes and different amines to give these molecules you see on the screen here, which worked for most of them in very high conversions, again 98, 99% in some cases. There are some that didn't work quite that well, pointing mainly to the ones here in the bottom row, where you had much lower conversions. So the two that I'm singling out here, they were actually done using, in the left case, using a ketone, not an aldehyde, which is much slower to react to form the initial coupling step first and form the imine. So that was only 57% in that case. And the other example on the right, in this case, we didn't use an aliphatic amine, but an aniline to form this molecule. And again, the aniline reacts a lot slower to form the imine first than some of the other amines do. And that's why we saw this drop in conversion. So we thought, can we maybe decouple this problem and decouple the two reaction steps involved, and therefore increase our conversion by using not just a single step approach, not feeding both reagents into our hydrogenator, but have a condensation step first. And that's exactly what we've done. So we put another flow operation in line before the hydrogenator, where we first reacted our aldehyde or ketone together with the imine. We did that at slightly higher temperatures, gave it more time, used a standard tubular type reactor system to form the imine at high conversions first. And then that imine was fed into the second stage together with hydrogen, and that was the hydrogenation reactor, to reduce it down to the corresponding amine. And for the two examples I just showed you, you can see on the right here, we achieved much, much higher conversions, 80% and higher for these two systems. Another set of reactions we looked into quite closely over the last few years were hydrogenations in the space of making fragrances and flavoring molecules. There's a lot of unsaturated, all sorts of double bonds, carbonyls in these quite often naturally occurring molecules. And depending on what hydrogenations you're performing, you can access a lot of other value products from these fragrance and flavorings molecules. The citral product tree is a wonderful example of this. So citral is the molecule here on the left with 3 double bonds, basically opens up, using hydrogenation pathways, opens up the access to a range of different other value molecules that then have different flavor profiles, going from more lemon type fragrance flavor profiles to more floral and herbal type systems, depending on the degree of hydrogenation and which parts of the molecule you hydrogenate. So we use these kind of systems to really look into selectivity issues and see which ones of our catalysts are selective to reduction of certain molecules, carbon-carbon double bonds or carbonyls. So these two are two examples of this. In both of those molecules, cinnamaldehyde and citronellal, you have an internal alkene and an aldehyde. And depending on what catalysts, what CSM catalyst we were using, we could either selectively hydrogenate the one or the other, or a mixture of the two. So what you see on the bottom is a range of different CSMs that were scanned for these reactions, all at the same reaction conditions. One of the main points to note here is that, for instance, the platinum catalysts that we used here are more selective to reducing the aldehyde and form those intermediates first, while palladium type catalysts are more selective to reducing the carbon-carbon double bond, and then would only later on reduce the carbonyl, the aldehyde in this case. Some of the nickels behaved similarly and had similar selectivities to palladium, although they were not quite as active as the palladium. Palladium is usually one of the most active catalysts. And just to complete the picture, the last one on here, the ruthenium catalyst, possibly had the worst selectivity of them all. But as you can see here on the right, it is one of the most active catalysts as well. So in the example of reducing citronellal, it produced a fully hydrogenated product in higher quantities than any of the other catalysts did. This is another selectivity case that was very interesting and where our study revealed quite some surprising selectivities. So here we hydrogenated linalool, which has an internal carbon-carbon double bond and a terminal double bond, which is much more active and much easier to hydrogenate. But most of those catalysts would really reduce both of those double bonds and show maybe a mild selectivity at best. So if you look at, again, at the palladium catalyst, that was one of the most active ones. Ruthenium, very similar as well. They didn't show much or any selectivity towards the terminal double bond. They reduced pretty much both at the same rate. Now, the nickel and the platinum catalyst was a lot more selective. There we saw more selectivity towards reduction of the terminal double bond. But what was very surprising was a new catalyst that we made by a radically different method, which is a bimetallic catalyst, nickel copper, which did not produce any of the fully hydrogenated molecules. So that one was 100% selective to only reducing the terminal double bond, which is a very powerful tool if you have selectivity profiles that you want to achieve. One further example I want to talk about is the semi-hydrogen of alkynes. Again, here the selectivity is key, and in this case you've got a consecutive reaction, so these alkynes can be reduced to the corresponding alkenes, but then all the way down to the alkane. And quite often the catalyst that does the first step also does the second step, while the value product quite often is the intermediate alkene, and that's what's used in the case of butyl-diol or methylbutanol. BED and MBE are those value compounds what industry is looking into making selectively for a range of different products, including APIs, vitamins, fragrance molecules again as well. So for this study, we again scanned a range of different catalyst coatings on our CSMs. And the three best ones are plotted here on this graph, where we have a NanoSelect is a particular palladium catalyst from BASF on a titanium silicate substrate. Lindlar is possibly the industry standard for this kind of selective reduction, which is again a palladium catalyst partially poisoned with lead. And then we benchmark that against one of our cold sprayed nickel catalysts as well. And what's plotted here is selectivity against conversion. So you want ideally be up in the top right corner, high selectivity, high conversion. Those catalysts, depending on what parameters we use for the hydrogenation, performed differently well for this reaction. The best one, if you look at just selectivity and conversion, is the NanoSelect. What was very surprising to us was that our nickel cold sprayed catalyst also produced very high selectivities and high conversions. And on the next slide, what we also wanted to look into is how productive were those catalysts. So here we plotted against the space-time yield, which is effectively how much material, how much product can you make per unit time, per unit reactor volume. And we wanted to compare our CSMs to what was published in the literature and what other people had done in various other hydrogenation systems for this particular reduction. And this is the reduction of MBY here. So those systems that we found were either PEG bed systems that others had used or stirred tank reactors or even monolith or capillary reactors. The data points here in green is the work from us, from our labs using CSMs. What you can see is that they have, compared to many of these other systems, very high space-time yields. In most cases, up to several kilograms of liter hour. And the best performing here was really our nickel cold sprayed catalyst that gave us up to 3.5 kilograms per liter hour in terms of throughput, space-time yield. One last set I want to talk about in terms of comparing this catalyst system to conventional catalyst system is a study that we've done earlier this year, where we basically compared the CSMs, or one-to-one, or as close to one-to-one as we could get, to a packed bed time system. So we used our CSM reactor. So in this case, the diagram on the top shows there's 10 tubes inside this reactor. We used one of those tubes and filled it with a packed bed using a commercial catalyst, palladium and alumina. And then in the other scenario, we used CSMs and coated the exact same catalyst and the exact same amount of catalyst on 4 CSMs and filled 4 of those tubes with them. The test reaction we ran here was, again, a simple double bond reduction, and obviously kept all the process parameters the same for those 2 test scenarios. Here is some of the data that we collected from this study. So on the left, the first I'd like to point out is looking at the pressure drop, and we've done that for different hydrogen to substrate ratios, is that if you're using CSMs, you effectively have no pressure drop for these type of reactions. We didn't measure anything, any delta P between inlet and outlet of the reactor when we used our system, which is expected because we've got an open and structured system that has a lot of void for the fluid to pass through it. While in the packed bed system, depending on the flow rate, you produced up to 8, 9, 10. In some cases, we had to stop reaction because the pressure was too high, 8, 9, 10 bar of back pressure. This is one of the big advantages of this system, where you effectively don't have to worry about back pressure production using these CSMs. But we also found that looking at the temperature profile, that the CSM outperformed the packed bed. If you think of all these hydrogenations, they're usually exothermic reactions, so they produce quite a lot of heat. And if we're stretching our catalyst over a longer length in a controlled fashion, then you also can avoid these hotspots and these increases of temperature, which can lead to unwanted side products. So what we measured here is the delta T, and looking at how much hotter the packed bed actually got than the CSM. And you see in those 2 curves that there is a very significant effect also. Using a CSM can reduce this delta T quite significantly. Both of them have an impact then also on the reaction performance. So what we did is obviously looked at the reaction outcome at our conversions and calculated that in terms of a turnover frequency, so the efficiency of the catalyst. What you see here is a ratio of the turnover frequency, the TOF, in our CSM reactor, as well as in the packed bed test case. And for smaller hydrogen to substrate ratios, so if we only gave it a little bit of hydrogen, the performance was very much the same between those 2 cases. But once we increased the hydrogen feed and therefore had a much more productive reactor, you could see that the same catalyst, again, we're talking about the same palladium and alumina, coated on the CSM was performing a lot better. In this case, we had a 20% higher TOF on the CSM compared to the packed bed. And with that, I'd like to just wrap up by summarizing what we think are the main benefits of this technology. So you've got, first of all, a tubular reactor system, which is a very good compromise between high process control, but also good scalability, taking this technology from a lab scale approach to an industrial application and production. We use additive manufacturing, not just because we can, but additive manufacturing has a range of benefits. It first of all gives the access to rapid customization of the mixer geometry. There's different mixer geometries for different applications and different fluidic profiles, but it is also very cost effective. So printing these mixer systems using direct metal 3D printing is more cost effective than making them with traditional subtractive manufacturing methods. And lastly, because this is a platform approach, we've been looking into deposition methods that are, again, industrially viable and scalable. But an immobilized catalyst has a range of different benefits. And with our deposition methods, we can address a wide catalog of different catalysts for a range of different applications. Reactions other than hydrogenations are mainly talked about hydrogenations today, but you can use these systems for oxidations, carbonylations, carbon-carbon couplings. And the sectors are, again, as I mentioned, throughout the whole chemical manufacturing sector, from fine chemicals, pharmaceuticals. At the moment, we're working also with clients on agrochemicals and others. Lastly, this slide is maybe just to give you an idea of where CSRO sits in terms of the custodianship of this technology and where we want to push it and bring it to. So we're currently working with various partners and technology providers to commercialize this technology. There's 2 companies here in Australia that we're partnering quite closely together with and are now licensees to this technology. Amiga Engineering is a specialized engineering company providing the 3D printing. And Precision Plating or Precision Catalyst is a specialized coating provider who is delivering the catalyst coating and is now also selling CSMs to anybody who wants to use them for R&D or production purposes. And the third licensee that we have is Merck, or Millipore Sigma, who's got a distributor license to sell CSMs as part of their online Sigma-Aldrich catalog. Aside from this, we're working also with a lot of other providers to complete basically the CSM value chain. So we're working on making bespoke reactor equipment that they can be used in. That's work in progress currently, but also process engineering and plant design to then put it into a final production scale application. And we're working with a range of chemical manufacturers that are now evaluating this technology for their purposes. Lastly, I also mentioned a lot of university partners. I've already talked about Oliver Kappes Group at Uni Graz, but there's many other academic groups that we're working together with in evaluating this for their purposes and for their chemistries. And with that, I'm coming to the end of my talk. I'd just like to bring up this slide and make the comment that this has really been, first of all, a fantastic journey for us, developing this from its first inception of the concept and the ideas all the way through the point where we are right now in bringing it into the market and working with chemical manufacturers to adopt this technology. And there has been a cast of thousands of people that I have to thank. Here on this slide is all of my colleagues that I've been working together with over the past few years. A lot of the students that have been working in our labs, developing new chemistries and evaluating the CSMs. Especially also a mention here to the University of Graz again, and Oliver Kappes Group. And for financial support, I'd like to acknowledge the Science and Industry Endowment Fund, as well as our commercial partner, Precision Plating. And with that, I'd like to close and finish my talk and hand over to Christiane and to anybody else who might have questions.
I'm muted. That helps, so you guys can hear me.
Yeah.
Thank you very much, Christian, for your presentation. Now we have got a attendee question. The question is: CSM seems to be better than packed bed. Are there any commercial CSM for lab scale and industrial scale?
Yes, there are. So what I mentioned on my last few slides, commercially available, there's 2 points or 2 sources from where anyone in the world can buy CSMs. It's directly from our manufacturing partner, Precision Plating. I can maybe bring up that slide again if you want, or there's a link in there as well. So Precision Plating are now manufacturing CSMs for sale, mainly in our standard sizes, but if there's a custom size that needs to be catered to, they would be able to do that too. And then for anything that is a standard or catalog item, they can also be bought through the Sigma-Aldrich catalog from Merck.
Brilliant. Okay, excellent. I hope that answers that question to that attendee. The other one was, what's the benefit of having an immobilized catalyst system compared to a slurry?
So slurry systems are quite often still used on small scale hydrogenation, such as in pharmaceutical manufacturing. In our case, we immobilize the catalyst on a 3D printed scaffold, and the catalyst never leaves the system. So that means a lot of the downstream processes that you would have to do if you have a slurry system are completely eliminated. So we don't have to do any filtration of the catalyst after the reaction, and any other cleanup steps that would have to be done if you had that in a large tank reactor. That's one of the main benefits. That it effectively gives you a much higher process intensification, process intensity. So it eliminates processing time, but also results in the end in a much smaller reactor for the same productivity or throughput.
Excellent. Thank you. I think that answers that question as well. I think we're almost out of time. So in that case, it's my turn to say thank you very much to Christian for your presentation. Thank you to all attendees for watching, and see you very shortly in the next session. Thank you.
Thank you.